Great. I'm glad to see you.
hmm I mean, that's not good. That means I'm having issues.
Listen, everybody has issues. Getting your issues resolved is the mature thing to do.
hmm
What can I do for you?
So I would like to start with the special homework.
All right. I'm going to grab that and take a look at it.
All right.
Is there a particular question that you need help with?
Um, I don't know how many I can ask you.
You can ask as many as you like.
Okay, then I would like to start with the first one.
Sure.
Yeah, I would like to and it's more about the proof section.
Okay. You understood how to write the statement as a conditional?
No, I didn't either.
Well, we need to do that first.
All right.
So, it's special homework number 5, and we're looking at problem number 1.
Yes.
And we're given this statement. Is the focus good?
Yes, it is. I can see.
Great. So it says the product of two odd numbers is odd. In fact, it says it is always odd, right?
Yes.
So we'd like to write it as an if-then statement, as a conditional, because once we have it written as a conditional, we can see the hypothesis that we will assume, and then we can also see what we wish to prove, the conclusion.
Mm-hmm.
What
So,
variables do you like to use for two odd numbers?
for two odd numbers, R and S,
Okay, so how do you think we could write this as an if-then conditional statement?
if R times S, RS, if RS is odd, no, if the product of two odd numbers is always odd, if the product, if RS is odd,
Uh-huh.
then the product is two odd numbers. I don't know, I'm sorry.
Okay, I'm glad you asked. It's talking about having two odd numbers, and then when we have two odd numbers, their product is also going to be odd. So it's saying if we start with two odd numbers, R and S, then their product, RS, is odd. Does that make sense? If
Mm.
R and S are odd, or
Oh,
you could say are odd numbers,
oh.
see, yeah, then R times S or RS is odd. Does that make sense? Does that help?
Yes, if R and S are odd, then RS is odd. Okay, yeah.
I mean, we have a shot at proving that, right?
hmm
Because now we can see that we will have this for our hypothesis. So we will assume this first part. And from that assumption, we will get equations about R and S. So we'll get our proof money by using the definition of odd. And then what we wish to do is prove this conclusion, but we'll be able to look at RS and do substitution using our equations, and we will be able to show what we wish to show.
Mm,
Does that help?
yeah.
Great.
But is that going to be for the proofs, right?
Yeah, I mean, in the proof, you will assume R and S are odd, right? We assume the hypothesis. And then we can use our thinking notes. We wish to show R times S is odd. Does that make sense?
Yeah.
I think you can do it now, right? Because you know the definition of odd.
Yes.
And
So,
how many parts to the definition of odd?
two.
Good. Very good.
But for the first, the A for the write the statement as a conditional introducing variables, that was only what you were looking for.
Yeah. I mean,
Oh, that's
you
actually simple.
right. But once it's such a simple step, right? But once we have this correct, whether you use A and B or R and S or X and Y, that doesn't matter so much. Just pick two variables, one for each odd number. And
Mm-hmm.
now we're going to be able to use the definition,
Do our
get
proof.
the nice equations, and we'll be able to use the fact that the sum of integers is an integer to get the product to look like 2 times an integer plus 1.
All right. So are we going to start by the definition of odd
Yes,
or it
by the definition of odd,
additional odd or
we have, or we
yeah
know, yep. And I like to kind of like, yeah, R equals what?
equals 2r+1.
Can't use R to define
Oh,
R. You need another
2
letter. Use
2k
K.
plus one.
Use K and J. Yeah.
Yeah.
2K plus 1. That's part one of the definition of odd.
And the S.
Well, let's
Oh,
finish the definition of
sorry.
odd for R
Where
first.
k is an integer.
Yes,
There.
K is an integer. You can write it with words, or it's perfectly fine to use our notation that K is an element of the integers, right?
Mm-hmm.
And then you will also get nice information about S, right?
Mm-hmm.
Because S is odd. But you can't use K for S, can you?
No, I have to use another letter. Maybe like 2g+1.
Sure, 2G plus 1. That's, see, we have,
Where g
yes, yeah,
g is a integer.
yes, G is an integer. And it's so nice because when we are careful like this, look, we have all this great proof money. It's like money. We just went to the ATM, the mathematics ATM, and we took out all this great proof money, and we'll get to spend it all. We're going to use all of this to to buy the proof. Shall we look at our wish one more time and clarify what will we have to do before we can say, oh, R times S must be odd. What will we have to show about R times S?
Substitute and do the algebra.
Yep, we're going to do the algebra, we're going to substitute, but I just want to point out that it's okay to revisit your wish to clarify the work that you have to do before, in order to get this conclusion. We wish to show R times S is, say, 2M plus 1, where M is in Z. See, that's the work we have to do.
But where did the M come from?
I just picked up a letter because I
Oh,
wanted to tell myself what R times S has to look like to be odd. So I needed another letter besides R, S, K, or G. I usually like to use M in my thinking notes. It's a multiplier here.
Mm.
But you could use F or X or Y or, you know, the letter we pick, all of these letters, that's not so important as the fact that we did choose letters so that our objects have names. And once they have names, we can write equations about them and we can refer to them. It just makes it easy for us to identify what we're talking about.
Okay.
And I'll leave the rest to you. I'm sure you can do the algebra. I'm sure your algebra is fine. And I'll just give you a hint. When proving m is an integer, we must use things we may assume. Remember, we had some things we may assume without proof.
Mm-hmm.
And in particular, uh, sums of integers are integers. We're going to have to use that particular fact.
But for the algebra part, the only thing that is kind of like that I'm kind of confused is about the fact that here we're using variables and we're not using any numbers.
It's okay because we're not going to get a particular odd number for RS. We're going to get an expression that shows RS looks like 2 times something I'm calling M here. It's not going to look like M. It's going to have K in it. It's going to have G in it. It's probably, you're going to do some multiplying. It's going to have it's going to be involved. It's going to be an expression because we're going to multiply 2K plus 1 times 2G plus 1 to find that R times S looks like 2 times something plus 1. And the algebra will show you what this something looks like.
So is it possible I can do it on my paper, then show you? Like if you can give me like,
Sure,
okay,
always. You can always take a picture and email it to me, or you can share your screen or just email it to me, and I will be glad to always look at your homework before you turn it in. That's
okay.
always an offer for.
But can I try this as an example
Mm,
right now?
sure.
Okay. So you said
I'll
that you,
pause the recording while you work on that.
okay.
We're just talking about special homework number 5, and we are looking at the first problem and sort of how to start that. Do you have a question, Sean? You're on mute.
Hello.
Hi, how are you?
I'm doing good.
I'm glad to hear it. Did you hear me that we're talking about the first problem in special homework number 5?
No, I didn't hear anything you said. I just joined.
Yep, we're looking at special homework number 5 where we start to write proofs. Were you in class on Thursday? Do you want me to pause this while you prepare your questions, Sean, or do you have?
No, it's okay. You can continue.
Okay, well, we're pausing for Karen to work on something. She wants to email me something to look at.
Can I show
That's
you?
fine.
Oh,
I can't see it like that, Karen. You're gonna have to take a picture of it
okay.
and send it to my email and I'll open it up on my phone.
All right.
Sean, do you have a question while Karen does that?
No questions for me right now.
All right, I'm gonna put this on pause and I'll wait to get Karen's email.
Okay.
So here we've done the algebra and we have satisfied part one of the definition of odd by getting R times S to look like 2 times something plus 1. And then we dealt with that M, which is our something, and we have shown M is an integer by using these nice properties that we don't have to prove, but that we can assume that products and sums of integers are integers.
Okay. Actually, I'm happy that we went through the algebra part because I totally skipped so many steps for the product part where we had to do FOIL.
Uh-huh, right. So that's one of the things that will happen as you get more hours of this kind of work under your belt. You will start to learn to be very careful. That's one of the most valuable things I think that you learn in this class is you learn to be careful. Because any kind of work you do where people are depending on you, it's very important to be able to check your own work and learn to ask yourself, is this right? Did I carefully consider everything that is important here?
Mm-hmm.
So, hey, you've just done all of your peers a great favor, and now they have solution to problem number one.
Oh, yeah. Yeah, I just needed to do the office hour with you to understand and have like a base because as you could see, I had some like um places where I was just confused. But now that you've explained this, I want to go through the homework by myself and try to do it and see in class tomorrow if I have any questions.
Okay, and let me just share the screen so we can look together. Let's look together at the other statements. So the second statement, I'm going to move this out of my, oh, that's not it. That's something we're working on. I would want to just to try to, so hard to move this out of the way. This up here. The second statement, you want to read the second statement? Can you see it?
Yes, I do. There exists a prime number p such that 2p minus 1 is composite.
Good. And I'm going to help you with reading that because the expression here,
Mm-hmm.
we read this 2 raised to the p minus 1,
Oh.
quantity minus 1, or whole thing minus 1 is composite. And we did a problem very much like this in class, but this is a little more complicated because I think we did 2 to the p whole thing minus 3 in class, but now we've got 2 raised to the p minus 1. So it makes it a little more interesting, and you want to show it's composite. So you will, and it's an existence proof. So that's easier because here we're just going to use scrap work and we're going to look at examples and
Oh,
try to,
yeah.
yeah,
You
existence
said,
proofs are kind of nice because they're examples that we can find the P that works. And then when we write the proof, just remember there are two things to do. We have to verify that our choice of P lives in the correct domain, i.e., when you pick your P, it's going to be a prime, but in your proof, you have to explain why you know it's prime. So you'll talk about that its only positive divisors are 1 and itself, whatever itself is.
mm-hmm.
And then part 2, you'll verify that the predicate holds. So you'll verify that this quantity, 2 to the p minus 1, is composite. You'll show that you can factor it into an a times b, and you'll verify that a and b are integers by just saying that. And you'll also verify that a is bigger than 1 and b is bigger than 1. You can look at the examples in the class notes, and that can guide you there.
All right, that works.
Now, problem 3 is another universal statement, so we cannot use an example.
We do if
But
then.
yeah, but it's already written as an if then to make it a little easier for you. In fact, we have 3 variables. We have an A that's even, a B that's odd, and a C that's even. And our wish is to show that this quantity is even. And I think you'll be able to do that now by carefully addressing both parts of the definition of even when you're trying to show that AB minus BC is even. Remember, the definition of even has 2 parts, just like the definition of odd has 2 parts.
Mm. Oh, I have a question.
Yeah,
So the first universal statement we did was to just say that it was odd, but here they're asking for two different they're talking about even and odd here.
that's right. So
So
we'll
we
have a bunch of equations. See,
mm,
A is even. You're going to get an equation about A and information about the variable that you use. So you'll need 3 variables. A variable to make A even, like maybe K, I don't know.
for
Then
the
you'll need a
hypothesis.
variable for B to be odd, like a different letter. And then you'll need another variable for C because it's going to have its own equation because it's even. But it's the same idea. You'll use those equations and use substitution
Hmm,
to look at AB minus BC, and it will turn out to be even.
I see. I see. And what about for counter examples?
Yeah, you know, the nice thing about counterexamples is that we're just proving an existential negation. When we're disproving a universal statement, we're proving its existential negation. So we give an example that proves the negation of the universal statement is true. Like this statement is false. The sum of any 2 distinct primes is always prime. That's false. There exist 2 distinct primes whose sum is not prime. So that's I kind of step you through it. First, I ask you to write this as an if then because it's universal. So, and I suggest how you can start that. There's a little something extra in this statement because I'm using the word distinct,
Distinct.
and
Mm.
that means the primes are different
Different?
from one. Yeah. So I suggest to you how to start writing, the if then. And then the negation, right? You have to be able to negate for all X and D and for all Y and F. If P, then Q. You have to know how to negate that. So I ask you just to write the general negation of this. It's in the book, so you can find it in the book. But I think if you remember, do you remember how to negate if P, then Q?
Yeah, it's gonna be P and not Q.
Exactly. And when we negate a for all, what happens to it?
Exist. There exists.
And then this one also switches to there exists.
Yeah.
So all that good work that you did to learn that is going to help you write the negation in general. And then you can apply that to write the negation of your if then. The thing to
Mm.
remember is the domain for P and Q, D is the domain for X or P, and F is the domain for Y, or here it's Q. That domain will not change in the negation. We are still talking about primes. So there'll exist a P in the primes, and there'll exist a Q in the primes, such that P is not equal to Q. That's our P of PQ, and the negation of the result, which is that their
Always
sum is prime. So the negation would be that their sum is not prime. So I step you through that. And
Oh
then,
yeah.
yeah, I kind of walk you through that process, and it'll just be a nice proof by example because you're going to be proving the existential negation.
But when you're saying indicate where you begin the counterexample, you want us to do the same thing we do for proof, like
Oh,
with the
that's such a great question. Let me show you. Uh, so for I think that's what is that number 4?
yes, it is number 4. No, sorry, it's not number 4, it's number 3, number
Is it?
3, C, number 3
Okay.
C.
Okay. So 3C, you'll just start it by counterexample. That's the way I indicate a proof by counterexample, as I say, or you can say proof by counterexample. You can do either one,
All right.
or you can do this, I usually just say counterexample, or you can say proof by counterexample. But that would be the way that you would indicate this proof is actually disproving the original universal statement. It's a proof, but it's a proof of the negation by example because the negation is existential.
Mm-hmm.
And then the last, now that is problem 4. It's section 3, but it is problem 4. I'll change this. Even though it's in section 3, the problem number is problem 4C. Okay, so the last section is, well, sometimes we're given a universal statement or an existential statement, and we have to decide if it's true or false. And if it's true, we prove it. And if it's false, we give a counterexample. Like that's another thing that we have to practice doing. And remember, we're going to have another lecture on Tuesday before the homework is due.
Mm-hmm.
But this is just a reminder about the definition that an integer x is a perfect square if x equals n squared for some integer n greater than or equal to 0. I don't even think I said n greater than or equal to 0 in class, but you can make that requirement if you want. And here is a little hint about what you would say to verify that something is not a perfect square. It means when you take the square root, that square root is not an integer. For example, if we take the square root of any of these numbers, since they are all perfect squares, their square roots are integers. Like what's the square root of 25?
5,
Yeah. And the square root of 36?
6.
Exactly. But if I asked you to find the square root of 20, that won't be an integer.
Oh.
So that's how you know 20 is not a perfect square. Its
Oh.
square root is not an integer. So I give you a little example. Notice 5, n equals 5 is not a perfect square because square root of 5 is not an integer. So here I give a statement, and it's a universal statement. It says for all m and n in the integers, if the product is a perfect square, then m and n are perfect squares. And the question is that true? Just because the product mn is a perfect square, does that force m and n to both be perfect squares?
Mm.
If you poke around with some of these different perfect squares and look at different ways to factor them as m times n, you'll find that you will be able to find an m and n where the product is a perfect square, but the m and the n,
Are not perfect square.
yeah, at least one of those will not be a perfect square. In fact, they will both be not perfect squares.
Mm.
When you carefully write the negation of this statement, we keep the hypothesis that mn is a perfect square, and we negate the conclusion, right? It's P and not Q. Well, the negation of this is not an and statement, it's actually an or statement. So you will only have to really argue that one or the other of these is not a perfect square. So I'm giving you a big hint. It turns out that this statement is actually false, and you should be able to find a counter example.
All right.
So Sean, do you have a question?
I was just gonna ask if we have a quiz this week.
Probably, probably on definitions.
Thursday, or I'm not gonna specify.
I'm not going to specify because I want you to come to class. We could conceivably have a quiz on Tuesday and a quiz on Thursday.
Right.
But certainly, it's a valid question. Are you thinking you're not going to make it to class?
No, I want to be in class. I'm just
Well, study what did we learn new? Definitions.
definitions.
Yeah, so let's just think about our definitions for a possible quiz.
Okay.
Okay.
Well, we have the definition of even and what else?
Odd.
Uh,
Odd. What else?
Prime?
Prime. Good. What else? If it's
Um,
not prime, we call it
composite.
composite. Mm-hmm.
Oh, I have a question. That's what I wanted to ask you. What does composite mean?
Okay, we'll go over that one. Let's
Okay.
finish our list. I think we also learned perfect square. So let's just review the definition of composite. An integer, it's got to be an integer, n greater than or equal to 2, so it has to be at least 2, is composite if there exist integers a and b such that, so that's part one, is that we have integers a and b such that n is equal to a times b. So that's part two, that n can be factored as a times b. You can think of your favorite composite number. What's your favorite composite number?
Uh, 32.
Great. So 32 can be factored as what times what?
32 can be 8 times 4.
Exactly. Where, and then the last part is that 1 is less than A and 1 is less than B. So when you pick 4 and 8, 4 is greater than 1 or 1 is less than 4 and 1 is less than 8. And we call those non-trivial factors. Because when you factor 32 as 1 times 32, that's called the trivial or sort of unimportant factorization of 32. But uh, just to write an example,
Please, can you show that I was writing?
oh, sure, I'll put it back up. My bad.
Okay, thank you.
Uh-huh. Composite numbers. Let's look at some examples. Thirty-two is equal to 4 times 8. 4 is an integer, right? 8 is an integer, and 1 is less than 4, and 1 is less than 8. So that's the complete, we've done everything, right? This is part one, is that they are integer factors. This is part two, where you actually factor the bigger number as a product of those two integers. And then part three is where you simply state, hey, I've picked numbers that are bigger than 1 as the important factors. See what I mean?
Mm,
Another example would be
Now,
something.
when you use the green pen, we can't really see when you use the green pen.
Thank you for telling me that. I'll stop using, thank you so much for telling me that. I will stop using the green pen. I will just make it black. Does that make it better?
Yeah.
Thank you so much. It's no good if you can't read it.
Mm.
Okay. And
Okay.
then another example we saw in class, and I can show it a similar one uh, to you again. If n is in the positive integers, so that means n is at least 1, then n squared plus 4n plus 3 is composite. That's a claim. So to prove it, we would just assume n is an integer that's at least 1. So assume n is nz plus. That means n is greater than or equal to 1 because the positive integers start at 1. So our hypothesis, I've got to stop using the green, is that n is a positive integer. So we would assume that. And then what we want to conclude, our conclusion would be to prove that this expression is composite, right? That's our wish. So we would assume n is a positive integer.
And we'll use the definition of composite. By the definition of composite, right after that.
We we do have to use the definition of composite. I don't like this. This is too close. I'm gonna move this down. It's too crowded. It's hard to read. Okay, so assume the hypothesis. So in our proof, assume n is an element of z plus. So n is greater than or equal to 1. In fact, I don't even need to put that in parentheses. It's just a fact. I can just write that. What do we wish to show? We wish to show, now let's look at our definition of composite, but we're going to apply it to this expression. So we wish to show that this expression is composite. So we wish to show n squared plus 4n plus 3 is equal to a times b, where a is an integer and b is an integer, and that 1 is less than a and 1 is less than b. Let's all, like this, we have to do all this to prove that n squared plus 4n plus 3 is composite, because that's what we wish to show.
Mm.
So we have to factor n squared plus 4n plus 3, and then we have to talk about those factors and why they're integers and why both of the factors are larger than 1. So let's do that. Let's do the factorization. So we want to factor n squared plus 4n plus 3. Can you factor that?
It's gonna be hmm. Oh yeah. It's gonna be n plus 2n plus no n plus
Do you know how to factor a quadratic?
um,
All right. So the number that goes the numbers that go here and here have to multiply together to be 3.
so one has to be 3, one has to be 1.
That's right.
Okay.
And they add up to 4.
Yeah.
And you can check this. This is n squared plus 3n plus 1n for a grand total of 4n plus 3. So this is the correct factorization. You can always check your factorization by foiling back, multiply it together. So we have our A and our B. This is our A, this is our B. So we have the first part. We've got it written as an A times a B. But now we have to talk about why n plus 1, that's our A, is an integer. And we have to talk about why n plus 3, that's our B, is an integer to get this part of the definition of composite satisfied. Then we have to talk about why each of these, A and B, is bigger than 1, why 1 is less than each of those. So it's
So
not hard to do because we know n is an integer. Since n, and we haven't used that yet, since n is in z plus, we know A equals n plus 1, right, is in z plus, and B equals n plus 3 is in z plus because
this product.
sums of integers are integers.
Mm.
We're adding integers together. N is an integer, 1 is an integer. In fact, I don't even have to put z plus here. I'll just put z. First of all, they just have to be in z. They don't have to be in z plus yet. But they will be. Do you understand why I said this part?
Because some of the others are integers, yeah.
Yeah.
We
And
don't say
then
sums and products because we
sums,
multiply them.
products, and differences.
Oh,
If you subtract two integers, you get an integer.
oh.
Yep. But when you divide an integer by an integer, you don't necessarily get an integer. So we can't say quotients of integers are integers because that's not true. The last thing we want to do is use the fact that n is greater than or equal to 1 to argue each of these two factors is, bigger than 1. 1 is less than A because n is bigger than or equal to 1. Right? Since n is greater than or equal
Yeah.
to 1, A equals n plus 1 is greater than or equal to 1 plus 1 equals 2. And of course, B, which is equal to n plus 3, it's bigger than or equal to 1 plus 3, which is 4. So 1 is less than A and 1 is less than B because A is at least as big as 2 and B is at least as big as 4. So these are what we call non-trivial factors. So n squared plus 4n plus 3 equals A times B, where, and you can do this, A comma B are in Z. You can put them together like that with a comma. And 1 is less than A, and 1 is less than B. So n squared plus 4n plus 3 is composite because we satisfied the three-part definition of composite, right? This is part 1. No, this is actually part 2, where you get it looking like that. This is part 1, where these pieces, these factors are integers, and this is part 3. So we have to satisfy all the parts of the definition of composite to prove something is composite. So that's a more complicated example than just 32 because we're using a variable, so we have to go through this sort of spiel. But I'm glad you asked because this reinforces something we looked at in class at the end of class, and that was sort of hurried. So I'm glad to have a recording of this.
True. Okay. Tomorrow in class, what are we going to talk about?
We are going to talk about some more proofs using even and odd, and we're going to talk
Okay.
about the definition of rational numbers.
Okay, that's good. Okay.
Yep, we're going to talk about rational numbers, and we're going to prove some statements involving rational numbers.
All right. I'll wait till class before I finish my homework so I can see how you do the proofs in class again. Just to,
Well, I think you have everything that you need to prove the things in the homework because The homework doesn't involve rational numbers at all. That'll be
Oh,
the next homework. The homework that I will give you to work on over
mm-hmm.
spring break will involve the definition of rational numbers, which we're going to learn tomorrow. And then Thursday, we're going to learn the definition of divides. I know you know that like 8 divides 32. You know that. But there's
Mm-hmm.
a formal definition of divides, and there's some interesting properties of integers involving divides. So we'll be exploring that on Thursday.
All right. That works for me.
Sean, do you have any questions?
Can you go over the definition of even and odd real quick and prime?
Actually, Sean, I'm going to let you refer to the class notes for those.
Okay.
Do you know how to find the class notes?
Yeah, I do.
Well, let me just share my screen and we can look together. I want you to start using the class notes as a tool, as a reference tool. They're one of the most important things that I provide for you. So on day 9, which was our last lecture,
Oh, okay. Yeah, all right, I see it. I'll go there.
there are all the definitions that we learned.
Perfect.
And we even talked about, the different parts of the definitions. So I guess you weren't in class on Thursday.
No, I was there. I'm only really asking because you wrote the definitions, but then you just skipped composite. So that's all. That's the only reason why.
No, composite is here. We discussed it.
No, I was talking about in the office hours, not in class.
Oh, I'm glad we didn't skip composite in the office hours.
Yeah.
Oh, you mean we skipped to
Yeah,
composite?
exactly. So I was just confused. That's all.
Huh. Okay. Well, I'm glad you're not confused anymore. You should definitely look at the class notes.
Hold
They're
on.
they're they're really important. I wonder why those are blank. It's weird. Wonder if they're just not showing up for some reason. Does it show up for you?
What, page 6? I don't see anything. No, it just ends on
But
page
I
5.
mean, when you go, do you see page?
Oh, let me
Karen, do
see
you
right
see
now.
page 6 when you look at the class notes?
No, I don't see
Um,
page 6.
I'm checking right now.
Nobody emailed me to tell me those pages were missing. Something happened, some kind of, a glitch.
I can only see page 7.
But
I can
so
see page C7. Yeah, I can see it.
you can see 6 and 7.
Yeah, I can see all the pages.
That's weird. Sometimes I'll just exit out of this. I'm just going to look at it myself. That's so weird.
Maybe to refresh the
I
browser.
think that's a great idea. I'm going to refresh my browser. Yeah, they're there. Okay, great. It's weird. Computers are funny. Okay, well, thank you so much for coming to office hours.
Thank you for the help, Mel.
I'll see you tomorrow in class.
All right.
Have a good night.
Mm-hmm.